AI research. Yann was last year at CLSP in 2008 and 2010, and at the time and still he was doing and is still doing research on vision, which has been an abiding theme through his research. But as I think most of you know, while doing representation learning for vision, he was carefully nurturing the flame of neural networks, now known as deep learning, until it blazed up again around 2006. Yann's PhD was from the Curie University in Paris in computer science. After that, he was at AT&T Bell Labs in Holmdel and Murray Hill. Murray Hill, right? Holmdel. First Holmdel. Okay, I thought you moved at some point. For quite a number of years. When he was in charge of the document and image processing group, he reported to Larry Rubiner, who CLSP people will know. And then a little more than 10 years ago, he moved to NYU. As I said, he's now, while he still has a chair professorship at NYU, he's also director of AI research at Facebook. And I guess you will be talking about work done on undergrowth auspices today? Yes. That's good. Okay, well, let's take one more together.
Thank you very much, Jason. It's a pleasure to be here. I think last time I gave a talk in this room, I can't remember how long ago it was. So apologies for being late. We can blame it on Abstract. It was probably the shortest preparation I've had for a talk right before giving it. Okay, so I'm going to talk about deep learning, surprisingly enough. Before, I'm going to say a few words, plugs, before those commercial messages. The first is for the NYU Center for Data Science. So this is a new center at NYU that I helped create for the last 2 years. And it's devoted to the extraction of knowledge from data, of course with the help of mathematics, computers, and statistics. And it has its own building on the main campus, or at least it will have it within a year and a half or so. I used to be the director, but I had to step down because of my job at Facebook, so now we're looking for a new director. And we also have 9 open tenure-track faculty positions if you're looking for a faculty position, particularly in natural language processing, for example. We're hiring. We also have positions for what we call data science fellows, which are kind of like super postdocs, if you want. All kinds of grants and master's program that started very successful, started last year, and we're starting a PhD program this year. The other plug is about Facebook. So about less than a year ago, I became director of Facebook AI Research, and which is sort of the first real research organization within Facebook. And the goal of Facebook AI Research is really to kind of push artificial intelligence. Internally we say we want to solve AI, but of course that sounds incredibly arrogant, so I don't, I only say it between friends. But it's really ambitious. So it's not just getting ads on Facebook a little better. It's much more ambitious than this. And it's a real research lab, open to the scientific community. We publish papers. We publish open source code. We have 2 locations in Menlo Park and New York City. We have 35 scientists and engineers, and we're growing fast. 2 postdocs, many PhD interns. We have a visiting faculty program also. If you're faculty on sabbatical, you want to spend some time at Facebook. And our projects span really the spectrum between the very long term, medium term, and kind of applications. We actually have things that are deployed at Facebook. And the research teams really cover all of AI, from the theoretical side and the mathematical side to all kinds of stuff that essentially is related to understanding content and understanding people. And we have a new website. Okay, so now let me go to the crux of the matter, and I'm going to go historical on you a little bit and talk about sort of the sort of recent history of deep learning. This is not so recent, I guess, but kind of explain a little bit the sort of trajectory that some of us have followed over the last 10, 15 years, maybe even longer. So in the early days of pattern recognition or machine learning, the way to do pattern recognition was to essentially take your input, run it through some sort of handcrafted feature extractor, and then plug a trainable classifier on top, let's say a perceptron. In fact, the picture at the bottom is the original perceptron from Cornell. We have, the sensor here, the feature extractor right here, random features, and the classifier at the right. Each module being a weight with actually a potentiometer with a motor on it. That's how the perceptron was built. It was an analog computer at the time. And of course, this model has been with us for a very long time, and you could say that most of the approaches or practical applications of machine learning these days basically conform to this model. Feature extraction followed by a relatively simple classifier. I would say a good 90% of applications of machine learning in the industry basically use logistic regression with a few tricks. Now, for things that are really complicated, like say speech recognition or image recognition, the pipeline for the last 10 years or so has been quite a bit different. It's got a few more layers in it. And here I'm drawing kind of the mainstream pipeline for speech and image, so at certain periods in the past. So you start with a fixed feature extractor, MFCC for speech, SIFS-HOG, or things like that for images, and then there is a stage whose role is to expand the dimension of the features to produce high-dimensional sparse representations, sparse features. And that's done using either Gaussian bumps or k-means or sparse coding or other methods of this type. Then, at least in the case of image recognition, there's a pooling operation which aggregates those features over space, and then it's plugged into a linear classifier. In the case of speech recognizer, the linear classifier is just the coefficients of the mixture, the Gaussian mixture Gaussians. And then you have, a graphical model to post-process. That model is being displaced, or has been displaced, at least for image recognition and speech recognition, by deep learning systems, which are essentially the repetition of a particular stage or module, if you want. Sort of multiple layers, all of which are trainable. With either purely supervised learning or a combination of supervised and unsupervised learning. And the future, or perhaps the present for some work, is to basically integrate the training of the entire system from end to end, not just the feature extractor, which you could think of as this part, not just the mid-level feature extractor, not just the classifier, but also the post-processing graphical model, language model if you use speech recognition, or something that makes sure the answer is consistent. And it's pretty clear where it's going. A combination of unsupervised and supervised learning to train very deep architecture of this type. Now, why do we need depth? We need depth because the world is compositional. In fact, Jason said a joke last night. He talked at Eclair last year, and he said this quote that I like very much. He said, "The world is compositional, or there is a God." I really love this. And so the world is compositional, particularly the visual world is compositional in the sense that local features, local patches of pixels in natural images do not cover the whole space of possible combinations of pixels. It's very, very correlated locally. And objects or large images are composed of combinations of those local features. And so representing images is naturally done by extracting local features and then detecting conjunctions of those features at various levels, right? So as you go up a level, you detect a new combination, a new set of combinations of features from the previous level. So that's kind of an intuitive reason why we need hierarchy for vision. But of course, we need hierarchy for all kinds of stuff. A lot of things are compositional, or at least we think they are. So not just pixels that combine into edges, text, emojis, parts, and objects, but also characters into words, word groups, clauses, sentences, and stories, as well as speech, of course. So now the question we're asking ourselves is how do we train those systems? And the problem that's being addressed here is not just training a classifier, but also learning good representations of the perceptual world. It's a question that people have been asking themselves, not just in computer science and signal processing, but also in neuroscience and cognitive science. How does the visual cortex build itself by just looking at the world? So it'd be nice if there were kind of a somewhat unified approach, some sort of simple learning procedure that would allow us to train this whole thing at once. And of course, we've had one for a long time. gradient descent backplot, essentially. But it's got limitations. Okay, so of course there is a little bit of biological inspiration in this whole story, in the fact that the visual cortex is hierarchical, composed of many layers. Or at least there is a model of kind of feed-forward processing, sort of fast visual processing in the visual cortex, particularly the ventral pathway of the visual cortex, by which the signal coming from the eye kind of ripples through a whole bunch of layers to go to the temporal cortex where objects are represented. And there is essentially no time. This process occurs extremely quickly in the human brain, less than 100 milliseconds. There's essentially no time for kind of complicated feedback and relaxation and generative whatever. So it's essentially a feed-forward process. So some of us, have been jumping on the opportunity to build very simple models of this, and essentially assume that the whole thing was feed-forward, which of course is not. There's another kind of more algorithmic argument as to why we need layers, and it's the fact that a lot of functions we want to compute, whether they are perceptual functions or not, are inherently sequential. So of course there is a theorem that will tell you that for any function of a finite number of bits, you will have a representation of this function in the form of two layers, either disjunctive normal form or conjunctive normal form. Right? You do a bunch of ands and a bunch of ors, and you can compute any function of a fixed number of bits. The problem, of course, is that most interesting functions require an exponential number of min-terms in the disjunctive normal form. And so it's impractical. In fact, most learning models are of this type. Support vector machines, current machines are of this type. There are two layers. Essentially one layer that does conjunction, another layer that does, you can think of it as disjunction, but not really. So there are functions that are intrinsically sequential, and you would think that by using multiple layers, you can save a lot on the number of stuff you have to compute, the number of intermediate variables you can compute. It's like, it's the same idea as factorization, right? If you have a polynomial, you can factorize it so that the amount of computation you're doing is less, have temporary variables. That's the idea behind having layers. There's really nothing secret to it. A lot of us have realized this a very long time ago. In fact, the early attempts at, back in the days of the perceptron, people realized very, very early that the next step was going to be having multiple layers. It's just that learning algorithms that work in this case just didn't come up until the 80s. Okay, so what are good features? What are we going to build or model out of? And a very simple idea also that goes back to the early 60s is that to kind of represent a set of inputs represented as vectors, the first thing you have to do is basically break apart the things that need to be broken apart. So things that are semantically different should be kind of easily separable in the representation space. And that can be done by a nonlinear function that will expand the dimension of the input. Okay, so we take our input, we're going to run it through a nonlinear function that's going to expand the dimension of the representation, and we have a chance that things that were previously aligned are going to get misaligned, things that were previously clustered are going to get broken apart. And so it's going to allow us to discriminate things that are different. Okay, but in the process of doing this, we're going to break apart things that should not have been broken apart, like say two different views of a single object, or two different views of a single object under different illuminations, for example. So the next step is going to be a pooling or aggregation that sort of glues back together the pieces that we broke originally. So here is kind of a very simple intuitive example. We have a bunch of 3s and a bunch of 8s, kind of flattened in this two-dimensional space, even though it's a much higher dimension. And the 3s and the 8s are very similar because the 8s are basically just a version of the 3s where the bubbles have been closed, the loops have been closed. So it's very difficult to kind of discriminate from the 8s and the 3 by just looking at individual pixels or distances between templates. So what we're going to do is we're going to do something like k-means. We're going to cluster the space into, in this case, 6 clusters, and here I've represented for each of the 6 clusters the samples that fall into each of those clusters. And so when a new point comes in, you figure out which cluster is closest to, say this one, turn this component on to 1, and set all the other ones to 0. Now you have one event code. And then you can do basically an or a max operation to kind of glue back together all the 3s and all the 8s. Okay? Very simple idea. So that's what we're going to do. We're going to build deep learning systems by essentially stacking modules, stages, that are composed of this nonlinear dimensionality expansion followed by pooling. So nonlinear dimensionality expansion is generally formed by 3 individual layers. One does some sort of normalization. That's actually optional in a lot of the current models. We don't use this. Then a linear operator that expands the dimension. And then a pointwise nonlinearity applied to the result. Okay, so basically just take each of the components of the result of applying the filter bank in this case and pass that through a nonlinearity. There are good arguments as to why this nonlinearity can be just pointwise. If you have questions about this, you can ask Joan Brunat, or who is currently a postdoc at Facebook, soon going to be on the faculty of the statistics department at Berkeley, or his advisor Stéphane Maillard. So we're going to take this. Of course, the learning is going to take place in the filter bank, and then we're going to stack multiple layers of this type. So the nonlinearity, the pointwise nonlinearity that people have come to use over the last few years is what we call the ReLU, rectified linear unit, which is basically max of x and 0, a function like this. And the pooling operation, the most popular one at the moment is basically just the max. So we do a max over, so it's like the small examples I showed, a max over inputs. So essentially, what a network is going to be is a bunch of linear operators interspersed with max operators, either a max of x and 0 or a max of several x's. And you could think of those max operations as being switches, right, in a way. That either switch x or 0 or switch one of the x's in the case of pooling. The training is going to take place through gradient descent, in fact stochastic gradient descent, technically subgradient descent, because of course those things are not differentiable, at least not everywhere. But it works. So we can compute the gradient by backpropagating gradients. That's an old trick. It's basically chain rule, but people didn't realize they could use this for machine learning until the late 70s, early 80s. And it's called backpropagation. I'm sure many of you know about this. Now the problem, of course, is that because those systems have multiple layers, the functions that we're minimizing look a bit like polynomials as a function of the parameters. Polynomials of high degree, in fact the degree is the number of layers, at least. And so those functions have lots of local minima. And it was sort of an argument against neural nets back in the 80s and 90s, particularly in the late 90s, when people said, okay, there is no proof of convergence, there is no guarantee that you're going to get any good results because you have so many, you have local minima, you're going to get trapped in local minimum. And people would, try out neural nets on kind of learning the XOR function with only 2 units. And, every 50% of the time, you would not converge to a proper solution. And so a lot of people kind of got discouraged of neural nets because of this. But that was a fallacy. So let me do a little bit of kind of fake theory. It's not. I'm not going to go into the details, but sort of give you an idea of how you can study the structure of the cost function of neural nets. So we have those deep architectures with ReLUs. And you can write the input-output relationship basically as a path integral, as a sum of a path of the contribution of each path. So each path essentially contributes to the output by essentially taking an input, multiplying by all the weights along the way, and then that's a contribution to the output. Now, along the way, this particular path may be active or inactive. It's active if all the units along the path are in the linear region, or it's inactive if the unit is in the 0 region, right? And so essentially you can write the entire function, the overall function, as a sum over a path, so this the sum of a p, of a binary variable, an indicator variable that indicates whether this particular path is active or not, and then the product along the path of all the weights along this path, right? And then you multiply that by the corresponding input, which is at the source of the path. Okay, now what we are really interested in is not the input-output function, but the loss function. And of course, we can use functions that are, loss functions are things like hinge function, hinge loss, like in the case of supervector machines, for example. So if you put a hinge loss is nothing more than another max of 0 and something, except it involves now the desired output in the hinge. And so we get, it's just another layer of ReLUs, essentially, with an extra input on the side. And so you kind of regroup all the terms, and what you get in the end is that the loss function essentially is a sum of a path of some coefficient, which is either 0 or non-zero, depending on whether the path is active or not. When it's non-zero, it basically wraps into it the values, the combination of the values of the input and the desired output. And of course, it depends on the weight, because whether it's active or not depends on the weight. And then you have a product along the path of all the weights. That's a polynomial of degree k, when k is number of layers. I shouldn't say k. L, where L is number of layers. And in fact, turns out a lot is known about the properties of such polynomials, particularly when they are normalized on the sphere. So people have studied this in the context of spin glass theory, or random matrix theory applied to spin glass analysis. It's called spherical spin glass. And what's known about those functions is that they have a ridiculously large number of critical points. Critical points being either local minima, local maxima, or saddle points. And so those things have an enormous number of saddle points, which is function of kind of combinatorial permutations and things of that type in the network. And so yes, those functions are very, 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 very non-convex. They have tons and tons and tons of saddle points and local minima. But there are two things that are interesting. First of all, most saddle points, the vast majority of all the saddle points, have an equal number of second derivatives curling down as they have curling up. Okay, so any saddle point you're on, you have a very good chance of kind of falling into a minimum. As the energy decreases, so as you go down in the loss function during minimization, you encounter more and more saddle points that have more and more dimensions curling up and less curling down. And the ones that are curling down have kind of a low curvature. And then at the bottom, you get local minima that essentially have all their curvatures curling up and maybe a number of them flat or slightly curling down. And in fact, one result from my colleague Gérard Benarous, who's the director of the Courant Institute, who's been working on this, is the fact that the local minima are all within a very narrow band of energy. So in a sense, it doesn't matter which local minimum you find because they're pretty much all equivalent. And in fact, we find that empirically. Empirically, you train a large neural net, particularly a neural net that's considerably larger than necessary, and you never encounter local minima problems. You always find a solution that is always pretty much the same error. It's a very different solution every time because there's lots of local minima, combinatorially large number, but they're all pretty much the same value, the same loss. So yes, it's non-convex, but it's non-convex in a non-nasty way, if you want. In fact, if you do systematic experiments by basically training a simple neural net, in this case here just 2 layers, with many different initial conditions with stochastic gradient descent, and you vary the number of hidden units, and you measure the loss on the validation set or a test set, you realize that the spread of value of the loss function as a function of the starting point is very narrow. Okay, and there are theoretical analyses, but the distribution of those critical points, which I'm going to do this one. Okay, now one of the things that has taken the world by storm over the last few years is convolutional nets. And I'm sure many of you have heard of convolutional nets. Basically, it's an implementation of the model I talked about earlier, where the linear operator is a bunch of filters, filter bank, right? So you take an image, you have 4 filters, you apply the 4 filters to this image through convolution, and you get 4 feature maps. You pass those through nonlinearities. In the case of this example, this is kind of a vintage convolutional net from the early 90s. It has, it's using sigmoids or hyperbolic tangent function, right? So you take the weights of the convolution kernel, compute the dot product with the corresponding window on the input, pass that through nonlinearity that gives you the output, and then you swipe this over the image, and you get a feature map. You do this for each filter, and of course we're going to learn the filters. The next operation is a spatial pooling. So the spatial pooling here takes a group of 4 pixels, computes the combination of them. In this case, the average. In modern versions, it's the max. But you step this window by 2 pixels so that the resolution of this window is half the resolution of the incoming window. And then you repeat the process. The second layer, second stage, I should say, each feature map here applies a different set of filters to each of the feature maps from the previous layers. The previous layer, add up the results, pass that through nonlinearity, and then it goes again through pooling and subsampling. And you can repeat this as many times you want. The basic idea behind this actually comes from neuroscience. It comes from the classic work in neuroscience in the 60s by Huber and Wiesel. Nobel Prize winning work. It's really kind of very classic. So it's the idea of simple cells and complex cells, the fact that the visual cortex has simple cells that detect local features essentially in the visual system, in the visual field, and then complex cells that sort of integrate the activations of the simple cells to kind of build a little bit of shifting variance in the detection. And the first person to implement this on a computer to kind of try to do vision with something that's inspired by this is Kuniko Fukushima in the 70s and 80s, early 80s, at the NTT Labs in Japan. He came up with this model called the neocognitron, but he didn't quite have the sort of proper learning algorithm to train them. So back in the late 80s, when I arrived at Bell Labs, I kind of implemented models like this. I mean, I had earlier version before that when I was a postdoc and PhD student. But I kind of was able at Bell Labs to kind of implement this in a big way, if you want, and apply it to real problems in handwriting recognition. So this was in the late 80s. So that's kind of a conventional net from the late 80s. Here's an example. This is an early 90 model. And it shows kind of the internal activations of the system. So here I'm kind of translating a 3, and you see the result of the first layer. That's the state. Each pixel is basically a unit. Then there is the pooling subsampling, then the second layer of features, pooling subsampling again, and third layer of features. And each vertical slice here represents, encodes, if you want, all the information within a 32 by 32 window on the input, and neighboring vertical slices in this map here represent different 32 by 32 windows shifted by 4 pixels. Here's a video. This is a younger version of myself from 1993. This is actually my phone number at Bell Labs in Mondale. And I hit a key, and it grabs the image and then recognizes the characters. So this is from 1992, roughly. And of course, the computer this is running on is a 486 computer, for those of you who were born at that time. And which, of course, had terrible floating point performance. And so we augmented the PC with a special purpose board with a chip on it that was actually manufactured by AT&T called the DSP32C, which was capable of the unbelievable speed of 20 megaflops. And that's what allowed us to kind of run this thing in real time, fast enough.
So was this the DX or SX? Do you remember? The DX had like a math coprocessor.
The 486 DX or SX? Yeah. We were not using the math coprocessor because we were running everything with DSP. But it would have been a lot slower on the. This is Rich Howard, who was our lab director. The previous gentleman is Donnie Henderson, who was one of the lab engineers. So we showed this demo to executive at AT&T, some vice president. He said, "Oh, that's interesting. And you mean you can add those numbers now?" Okay. Right, but of course the problem, very soon we realized recognizing individual characters was not really kind of the most interesting thing. What you have to do is recognize words and sentences, documents, and things like that. And so we figured pretty early on that the solution to this was to steal a bunch of ideas from the speech recognition people, and particularly people who are working on discriminative training for speech recognition systems, and basically build a graphical model. It wasn't called graphical model back then, on top of essentially a recognizer to train it discriminatively simultaneously so that the system would be able to recognize entire words without being told where each of the characters are. And so I kind of represented it this way here. You could think of kind of a whole system where you show a word image, and perhaps it's pre-segmented, perhaps not. You go through a convolutional net or several copies of a convolutional net, which formulates character hypotheses. So it says, I think there's a character here for that category, and it reads a score. It could be this other character, that score, etc. Then, of course, there are some constraints on word geometry, right? You can't have two characters at exactly the same place and things like that. So there is some sort of, latent variable here that would be kind of the segmentation of the string that you want. And that's, some sort of graphical model. So that produces word hypotheses, and on top of that, you have a language model that kind of figures out what's the proper sequence of characters. And you can formulate all of this as, likelihood maximization or energy minimization, which I really prefer. And so basically, given a word image, find the combination of a segmentation and a word output that minimizes some energy that we train appropriately. And that resulted in a practical system to read checks. I'm not going to go right now through the process of how we trained this. I'll come back to this later if I have time. But this system could read checks and was deployed in 1996. At some point in the late 90s, it was reading 10 to 20% of all the checks written in the US. So they were written, they were read by convolutional net. And then two interesting things happened. AT&T proceeded to break itself up into three companies. One company was NCR. It was the company that was actually using this in practice and selling this to banks. The other company was Lucent Technologies, and the third company was AT&T. The product group went to NCR. The development group that was doing all the engineering for this went with Lucent, and the research group, which became our group, stayed with AT&T. And so the whole effort on the very day that we were celebrating the deployment of this was basically disbanded. And then by then, nobody in the machine learning community was interested in neural nets anymore. Within a few years, neural nets basically just disappeared. And so I stopped working on this. I worked on other things, which I'm going to talk about. But okay, so one thing that we realized back then was that it was very easy to, as I showed in one of the animations I showed earlier, it was very easy to basically apply a convolutional net with a sliding window over a large image. It doesn't cost you, unlike many other techniques of this type, or recognition techniques, you don't actually have to recompute the entire neural net at every, or the entire classifier at every location. If you want to compute the output of a convolutional net over several locations, you simply make the convolutions bigger. Just feed a larger image, resize the feature maps and everything so that they have the appropriate size for whatever convolution you're doing. Do this all the way through, and interpret the last layer not as a fully connected layer, as people sometimes call them, but as yet another convolution, so that the output is also replicated. So the animation I showed you, I was telling you, each slice of the feature representation represents kind of a 32 by 32 window shifted by 4 pixels. It's an example of this that we used to call space displacement neural nets, but it's just a convolutional net. So then you plug, so you have the detections, the various detections for those kind of windows at the various locations indicated here. The winning category is indicated here. You feed that to a very small little Markov model, weighted finite state machine, to pull out the correct interpretation, and it gives you the correct interpretation. There's no explicit segmentation here. It's just raw image, convolutional net, little weighted finite state machine. That's it. There's a bit of a revolution to think that you could do multiple object recognition without explicit segmentation. Of course, speech people know this because it's on this floor. But image people know. You had to kind of pre-segment. Segmentation was an entire subfield of computer vision. It still is, actually. So you could do things like this. You have kind of pretty sharp transitions between ambiguous characters here. Right, so pretty soon we realized we could use this for object detection. Back in the early 90s, in fact, we worked on face detection. And it was very successful, but this work was completely ignored by the computer vision community. They don't even know about this paper. They kind of vaguely heard about this one. But by then, another set of techniques were very successful for face detection in the computer vision community, the so-called Viola-Jones technique, which uses boosted cascades and stuff like that, which is what's built into your digital camera, basically. But this actually worked better. It was a little slower, but it worked better. That's my grandparents' wedding. And more recently, we kind of applied this to things like pedestrian detection. So this was about 5 years ago. We started working on this, and we had really good results. In fact, that's an application in which we use a combination of unsupervised and supervised learning. We got really good results. At some point, we actually had the record for pedestrian detection. But still, the computer vision community was not convinced that convolutional net was a good approach. So it's a fluke. We can do better. In fact, they could do better. There were better classical methods now. So we tried to apply this to object recognition, but of course, for a long time, there was no real good data set for this. So we do things like, road sign detections, or this is a data set from Google, the so-called Street View house number data set. So, and then, back in the early 2000s, I built my own data set, which had kind of a relatively large number of training samples, but they were kind of semi-artificial images. So these were kind of toys that with pictures are taken along several angles, and then we slap them artificially onto different backgrounds. Classical vision methods just completely break down on this. convolutional net do fine. Okay, but again, the computer vision committee was completely uninterested by this. And then they started getting interested in object recognition. And so this data set, the Caltech 101 data set, was collected by Caltech. And it was composed of 101 categories and only 3,000 training samples, about 30 training samples per category. So it's a very, very small data set. And people, started kind of try different techniques on this. And one of the techniques in the kind of mainstream approach to computer vision that eventually worked reasonably well on this was to essentially detect features densely on the image by basically doing SIFT or something like this, or HOG, extract the features densely on every patch, and then feed this through one of those dimensionality expansion, a pipeline, and then some sort of spatial pooling, and then a simple SVM classifier on top. And that would give 65% correct, or something like this. This is the work by Lena Zednik and Jean-Paul Schmidt around 2006. So we tried convolutional nets on this, and we tried a convolutional net of the type that we use for handwriting recognition, with just higher resolution. And the performance was ridiculously bad. It was 30% correct when the competition was 65% correct. That was really embarrassing. So we started playing with the architecture a bit to see if we could improve this. And eventually we figured out that if we replace the average pooling by max pooling, all of a sudden the performance jumps to 60%. So that's a pretty big difference. Just a very kind of different nonlinearity. If we replace the sigmoid by an absolute value, but still keep average pooling, you still get about 60%. So the idea of having kind of a harsh nonlinearity or rectification really makes a huge difference when you're talking about image recognition. And then with various tricks, once you provide pre-training and blah, 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 we could, contrast normalization, we could get to 65%. Of course, by the time we got this, the sort of mainstream approach was in the low 70%. And so we were kind of always 5% behind the kind of mainstream approaches. I also worked on the mainstream approaches and actually were among the ones who got, about 70 or 80%. And it's simply because the data sets were too small. So we worked on other applications for which we had more data, things like biological image segmentation or robotics. So we had this, I'll show you a video at the end if I have time. This little robot driving itself around, basically using a convolutional net to label an image, basically label, again, using a sliding window approach, it would label every pixel in the image as to whether it's traversable or not. Okay, so you train it on lots and lots of data collected while the robot runs around. And you're training to kind of determine whether something is drivable over or not. And it's it's very cheap to apply the convolutional net to the center image and generate those traversability maps. Yes?
Is there any technical reason or justification as to why max pooling is so much better than average pooling?
Not really.
In particular, relating to all of the local minima story that you told us earlier?
No, short answer is no. There's no clear, there's sort of, two-dimensional wavy kind of things. If you have max instead of sigmoids, so first of all, there's a problem with sigmoids, which is that they saturate. And so when they start saturating, if you have too many layers, the gradient descent doesn't work anymore. Whereas with the, somehow it doesn't happen with the resonance. We don't quite understand why. The other advantage of max pooling is that it breaks the symmetry. So when you have, you can think of max pooling as a switch. And so when you backpropagate the gradient, only one of the contributing input gets a gradient, the other one gets zero gradient. And that drives the system towards specialization. So it sort of, makes it easy to, there's sort of a connection with this and the problem of breaking symmetries to kind of, get around, finding a good side on the cyber point. It's all about symmetry breaking. You have to, the system has to find ways to spatialize each unit to do something that's complementary with all the others. If they all do the same thing, it's a cyber point, basically. And so they have to be kind of asymmetric, which is why you have to initialize those networks with random values, otherwise they're symmetric and they never take off.
Is there any connection with my last story about the fact that every layer needs to be a contraction, and therefore when you have maxes, you do get a contraction, but when you have just averages, you don't?
Well, it works with L2. It works with LP. Max is just LP. So there is, you need a rectification. That's the I guess that's the one. But yeah, there's a huge connection with Stefan Maller's work. In fact, the scattering transform is very much inspired by convolutional nets, and there's a lot of connections between, which is why I hired this former student as a postdoc. Okay, so the other thing that we worked on was semantic segmentation. So this is, in some ways the ultimate vision problem, where, you want to label every pixel in the image with the category the object it belongs to, right? So you have sky and tree and field and river and people and windows and buildings, etc. And we use what's called a multi-scale convolutional net for this, where, so again, you can apply this sort of sliding window approach where one particular output here in the output map is influenced by a 46 by 46 window on the high resolution input, where we have 3 copies of that convolutional net with the same weights, the shared weights, applied to lower resolution versions of those images, and the features are combined in such a way that to make that decision for that single pixel in the center of that window is actually looking at the entire image. Okay? The classical way in computer vision to solve this problem is you have a relatively local classifier, a relatively simple one, has features and an SVM on top. And then you have a very complex graphical model on top to make sure the decisions are consistent. Here we make sure the decisions are consistent by looking at a very, very large input window to make a decision for every pixel. And there's a little bit of post-processing, which is kind of a voting over superpixel boundaries, over superpixels. And this works amazingly well. So we basically beat the record on 3 different data sets for this that a number of other people had tried as well.
Sorry, I didn't get how the convolutional net is integrated with the superpixels.
Well, okay, so you do a superpixel segmentation over the image, okay, and then you take the output of the convolutional net and you make a majority vote over each superpixel. So each superpixel is categorized as a whole as the category that has the largest score, overall score within the superpixel. It's very simple. And that's what gives you the highlighted result here. You can do slightly better by using those complicated CRS on top. The same people, the same techniques that these guys are using, but it doesn't make much difference. And it's much slower. So not only is this the best method, it's also the fastest by a factor of 100. Because you don't need inference of a graphical model, it's just a feed-forward thing. So we submitted this to CVPR, and it was soundly rejected by people who said, what is this convolutional net stuff that nobody has heard of? I decided at that point I would not again submit papers to computer vision conferences because it was a complete waste of time. And so I wrote a public letter that was published at the debate conference. Eventually we published this in PAMI a couple of years later. And I don't blame anybody because that's just the way the community is. I used to be, I was program chair of CVPR as well, so I'm part of the community, but it's just, at the time, the mindset of the reviewers was such that you just could not get anything through. A lot of my students suffered for that. This is a video, again, of applying the system. This is just frame by frame, so there's no temporal consistency or anything. We can actually run this in real time on some sort of FPGA device. It makes some stupid mistakes, like those beige areas are sand, and this is the middle of Manhattan, so there's no desert, as far as you can tell. But it works okay. We can use we can do a little bit of temporal consistency to get the results better, and that's in a couple of papers.
But why wouldn't you just take the output of the narrow net at every superpixel and just use it as a unary term in the conditional random field?
Yeah, that's more or less what was done for the bottom lines. Yeah. It's using a tree. It's fairly sophisticated actually, but it doesn't make a huge amount of difference. That's the problem. Okay, but what about real object recognition, right? So what happened? Then something happened in 2012 that completely changed the mind of the vision community with respect to those models. And what happened is 2 things. First, the appearance of the ImageNet dataset, which had 1.2 million training samples, not 1.5, it was 1.2, with 1,000 categories, and there was some sort of formal competition that people participated in. And then the second thing that happened was the emergence of fast GPU capable of over 1 trillion operations per second. Our friends at University of Toronto, Jeff Hinton, Alex Krzyzewski, and Ilya Sitzkever, Alex Krzyzewski in particular, had very early on had a very efficient implementation of convolutional nets on GPUs. Several people before that had GPU implementations, but not to the same level. In fact, the first people to do this were at Microsoft Research. Patrice Simard at Microsoft Research in the mid-2000s had GPU implementation of convolutional nets. And the data set, has, fine-grained categories and relatively easily confusable categories. When you have 1,000 categories, you can have things like, breeds of dogs and stuff like that. And they used a very deep and very large convolutional net, at least by the standards of 2 years ago, with 800 million connections, about 60 million free parameters. So you have fewer parameters and connections because of the weight sharing in the convolutions. And this sort of curious kind of architecture, which turned out to be kind of a local minimum for performance, if you want, local maximum for performance. And this thing worked amazingly well. They managed to get 15% error. So an error is counted when the system doesn't give you the correct answer within the top 5 among the 1,000 categories. So they got 15% error with that metric, whereas everybody else was getting 25%. And that, everybody was stunned. It created nothing short of a revolution in computer vision. The features that were run by the system look really nice. We had features like this also for other tasks, but those were particularly nice. Very, very soon, Google deployed, Google kind of bought Jeff Hinton and his 2 students, and they very quickly deployed an application for image search based on this, which works pretty well. So this is kind of a search of my Google Plus photo collection where I type bird, and most of the hits are birds, except for octopus and radio control model airplanes and Sami Benjo. The weird thing about Sami Benjo is that he actually works on image recognition and deep learning at Google. So, like, smells like an Easter egg. But he says he just looks like a bird. A few months later, some of us managed to also have pretty fast implementations of those things on GPUs. We're taking a different tack of actually implementing those things on FPGAs and large collection of CPUs before that, and participated in the next competition. So this is a system called Overfeed. If you type Overfeed NYU, you can download the code. It's not the code for training; it's just for running. And there's 2 different networks, a big one and a small one. The filters look very similar. So this is kind of an interesting chart that shows who was using deep learning or convolutional nets and who was not using convolutional nets in the ImageNet competition for classification. And this is 2012. Only the Toronto team used convolutional nets. The other people used more classical techniques. And the performance gap was huge. And then the next year, pretty much everybody used convolutional nets. Most of those people use some hacked version of the Toronto code, actually. And 3 of those entries are actually from NYU. So this is the Overfeed system, which I told you about, the Ziller-Fergus network, and this is Clarify, which is a company started by Matt Ziller right after he graduated, just before the competition. And then this year, basically everybody is using convolutional nets, and the error rate has gone down by another factor of 2 from last year. It's pretty amazing. It's pretty dramatic. There's a bit of affiliation between this Google net. Well, it depends who you are. You pronounce it in different ways. Like Google net, but I guess we always just say Google net. And there's a bit of affiliation between Overfeed and Google net because my student Pierre Samanet, who kind of was the main person on this, was also part of that team.
Can you say more about what happened between 2013 and 2014?
Bigger networks, longer training. There is a trick that the Google Net team used, which is this kind of repeated set of 3 layers. What's more interesting actually is the VGG team. So this is the Oxford Unreasonable group. They came very close, and they use a very deep network with many more layers, with very, very small kernels, essentially a bunch of 3x3 kernels all the way through. So what it seems to show is that what you want is lots of nonlinearities in the system, basically. So it works really well. You can do, okay, but one problem, of course, you want to do is localization, not just classification. So how do you localize? Well, what we did with Overfeed, what people are doing as well, is you take the image at various scales.
Quick question.
Yes.
That 7%, how much would it change if you ask it to be in the right class rather than just being within the top 5?
It's in the 30s, 30%, 20, upper 20 or low 30s. I can't remember the exact number. Yeah.
And if I ask for the second best, would the category be something related or something that makes no sense?
No, it's related. Yeah, it's very much related. Right, so to do localization, you can do the sliding window approach on multiple scales, and what you get is a heat map for each category, right? So this is the bear category, and you get a heat map for whether there is a bear, within this window, more or less. So you can, do the sliding window, and then you can do some sort of non-maximum suppression or voting mechanism to figure out where it is. But that doesn't give you accurate answers. And so what we did was to train the system to also produce an extra set of outputs that would predict where the bounding box is. So if we have a network looking at the head of the bear, it can actually predict where the bear is, where the bounding box of the bear is. And so we trained this network to actually predict where the bounding box would be. It's only one set of 4 outputs for all the 1,000 categories. It's amazing that it works at all. So this is a plot of where those boxes are predicted, where, yellow box is a bear and the red box is something else. And at the end, you get a nicely trained bear. It works for all kinds of weird animals of various types, and you can also do detection. So detection is the same stuff, exactly, except now you allow multiple objects to be detected instead of only one. It's some sort of threshold. So the ground truth is the top right, and the answer of the system is there on the left. So it works pretty well, even when the objects are overlapping. So again, no need for segmentation prior to recognition. It's done simultaneously. It works really well for burritos for some reason, for various other things. And these are the competitions, the results of the competition for detection. We mentioned that 2013, and this is sort of the middle of the year. There's a lot of competition for that. And then 2014. And so we placed third there because we didn't have time to train our system. With a couple more weeks of training, we managed to get it to 24, which was above the winner. But then within a few months of this, the Berkeley team managed to get 34. They used a different technique that kind of focuses on areas of interest. But again, there is a kind of a similar technique. But they, that performance is actually not that great by the standards of, I can't fit those two. By the standards of today, the Google and Net team again got 43.9%. This is mean average precision, so larger is better. So this works really well. Actually, rather than bore you with crazy pictures, let me show you the demo of that system. So I have a webcam in my hand. And what you see here is the result of the network. So if I point it as here, it says notebook, handheld computer. Sounds about right. Screen, CRT screen, spacebar, yeah. Computer keyboard. Faces? To watch, yeah. Okay, it knows it's glass, right? Sunglass, okay, that's about right. Let's see what else. There's another screen here. Screen. Okay, I've got 2 phones here. The right phone. I think it's the reflection from the lighting actually that screws it up. Okay, iPod. Okay, that's more like it. It's actually not an iPod. It's a Samsung Galaxy S4. I actually gave this talk at Samsung. Pardon?
Wait, your jacket? It's total bad, the jacket.
The jacket?
Yeah, it's on the table.
What about it?
Just shoot the camera.
Oh,
exactly.
okay. I don't think it's going to say anything interesting there.
I just saw that.
Electric switch, that's terrible. That's absolutely terrible. Defense camera, yeah, because it looks like a
It said backpack as the fifth
see, what about you
suggestion.
guys? Well, the lighting is completely washed out. I really don't. Okay. Restaurant. Okay, that would be. Yeah, the lighting is so strange. It's probably the setting of the camera actually, but not so successful here. Let's see. I'm liking other implements of various kinds. Maybe shoes. Yeah, shoes. It doesn't actually know
It's also a diaper.
You have to hold the camera pretty still because otherwise you get blur, motion blur, and then it's garbage. Okay, so this demo is different. This one I can train, so I can point the camera at some place and then click a button to classify it. So I don't know what this thing is, but I'm going to declare that's class A. Okay, and you guys on this side, you're kind of washed out. But I'm going to declare that you're class B. Okay, I'm going to be class C. So every time I click on the Learn button, it kind of records a template at the top layer. So it takes the features at the top layer and it basically does kind of a nearest neighbor classification if you want. And every time I click the Learn button, it records a template for the nearest neighbor classification. Yeah, I really apologize for the lighting here. It's pretty terrible. Okay, so the left side is class B. The right side is class B. This thing is class A. And class C. And I need only a few samples to train this thing for a new category. There's quite a bit of invariance. So as you can tell, I can move the camera around, change the size for a bit, maybe change the background, change the angle, somewhat. So there's a lot of built-in invariance, if you want, that are due to the fact that the system has been trained on a lot of different examples with the idea that things are supposed to be.
So you don't train the features, and you just do the top layer.
I chop off the last layer and I train templates on the top. Yeah. In fact, so people have done this. There's a group in Denmark that has. Yeah, it has astounding in the title. Yeah. So they took our overfit network, chopped off the last layer, and retrained the top layer on tons and tons of different data sets from computer vision, and got pretty much state of the art on every single one of them. Except a couple, like recognizing the Oxford building. It was kind of a little bit old. So that's kind of interesting. You get, really good generic features. Another technique that we developed about 20 years ago, and that has resurfaced over the last few years, is what we call the Siamese architecture. So the idea here is to do metric learning. So if you have a task where you don't have all the categories at training time, so you want to train the system to give you a similarity measure between objects. You take two copies of the same convolutional net that share the same weights, and you show it two objects that are the same category, and you tell the system, produce outputs that are nearby, and when the two objects are different, you tell it produce outputs that are different. Push them away, essentially. And recently, my colleagues at Facebook, Yann LeCun and Min Yang, have used this to do, as one of the techniques to do face recognition. And so it's called deep face. It was developed at CVPR last year. So they take a face, they do face detection, center it, and then feed it to this convolutional net, which actually has no shared weights at the top layer, and then train it first as a classifier, then fine-tune it using this metric learning technique. And they get really, really good results with this, on par with human performance. Those systems actually are used at Facebook to do face recognition. More recently, a student, visiting student, Joris Montar, spent time in my lab and worked on using convolutional nets for stereo reconstruction. So here, he trained the convolutional net with two inputs, two image patches, to tell us whether those two patches match in the left and right image. So it's basically a two-class classifier. Do those two patches match? Are they the same objects just viewed from the two cameras? And it works amazingly well. So with this, we can compute disparity, run this through a post-processing to smooth it out, and he basically beat the record. So he got 2.61% error, where an error is counted if you get disparity wrong by more than 3 pixels. Actually, so the CVPR deadline was Friday, and just Thursday, someone anonymous published a result that's just slightly better than this, requesting a figure than using convolutional nets. So this works really well. There are other things like body pose estimation. This is work by Jonathan Thompson at NYU, which I can show you here. Together with Chris Bragler and Arjun Jain. so this is the system running. There's a depth camera that captures the hand, and there's a convolutional net that detects all the key points on the hand, run this to an inverse kinematic model, and all in real time resynthesizes a synthetic hand that reproduces the pose. And so these are the heat maps that are generated by the convolutional net, and then that goes to an inverse kinematic model, so you can do real-time puppeteering essentially. I'm going to skip this and that. One thing so we did some work on hardware, but I talked about this last night in here. The last thing I want to say, actually, I want to skip this as well, is talk a little bit about some recent projects that have been going on at Facebook. And here we go. So this is not my work. This is work by my colleagues at Facebook. And a lot of our work is focused on natural language understanding. And I know there are many people here who are interested in natural language understanding and speech. And so this is work by Keith Adams, Sumi Chopra, and Jason Weston to predict hashtags. So you make a post on Facebook or Instagram or something, let's say on Facebook, and you can type hashtags that are supposed to kind of indicate the category of your emotional state or the kind of stuff you're talking about. And we trained a deep learning system, basically a convolutional net operating on word encoded as vectors to predict the set of hashtags that are likely to be relevant for a particular text. And it works actually quite well. So well, in fact, that it's usable. We're also training a fairly large deep learning system, recurrent neural nets in particular, to predict posts and comments. And so we can initialize those by typing just a few characters, and then we can just let them run. It's a recurrent neural net that just basically produces characters one after the other. And this is trained on the corpus of Facebook posts. And of course, it's nonsensical, but it sounds sort of like colloquial English, more or less. In fact, the perplexity of this model, viewed as a language model for English, trained on a standard corpus, is actually very, very good. Close to the absolute accurate. Another very interesting project is by Jason Weston, Antoine Ball, Jason Weston, and Sumi Chopra, is on question answering systems. So here the problem is you have a knowledge base represented by a graph, which basically is a bunch of entities and relations between them. And then the system is supposed to answer questions. So you type a question, and you have to look for the graph for possible answers. And then there is a learning system that basically embeds words or sentences that tries to figure out which answer is most relevant to the question. And the secret to this is to do a simultaneous embedding. This is something Jason Weston has been working on for a while, where you embed questions and answers in the same space so that an answer that's relevant to a particular question is are represented by vectors that are nearby. And if you show an answer that's not relevant to a question during training, you can move them away. So it's very similar to the Siamese net stuff I was talking about earlier. It's a different loss function, but it's a ranking loss, but it's a very similar idea. And just very simple kind of ranking training actually beats the record on one of the standard data set for question answering. And so you can answer questions like this. This is from Freebase. This is the type of questions. So the first is the correct answer, and then the second bracket is the answers that are produced by the system in response to the questions. Exactly. So it works pretty well, and it's got really really good accuracy compared to alternative approaches to this. So another technique that Jason and his colleagues have developed is a technique that basically attempts to give common sense to machines. So what do you think common sense is? So if I take an object and I let it go, it falls, and it's going to fall. If I throw it, you can predict the trajectory and catch it if you're good enough. Or if I say Jason stands up, picks up his laptop, and walks out the door, then if I ask, is the laptop in the room, you say no because he walked out with it. So you have this sort of mental picture of what's going on when you told the story, and you kind of maintain a state of the world because you know what the constraints of the world are, right? Either the physical constraints or other constraints, right? And so that's what one of the possible definitions of common sense. So how do you teach common sense to a machine? It's basically by showing it questions and answers, and then have kind of a simulator of the world. So imagine you are in a text-based adventure game, say, that uses Lord of the Rings or something like this. And the machine is trained by basically observing the state of the adventure game, and then being told events, and then being told answers to questions. And after a while, it kind of learns, what the association between all those events are. And so after a while, you can do things like tell it the entire story of Lord of the Rings. So spoiler alert, sorry if you haven't watched it. Okay, too late. Okay. Really, it's a whole story. That's the only thing that happens in the movie. So, all this, people travel to the cave, don't drop the rings there, blah, 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 blah. And then at the end, you ask a bunch of questions like, where is the ring at Mount Doom? Because Frodo dropped it there. Whereas people now at Grey Heavens, etc. So the system, has kind of a mental model of what's going on. So we call this, or they call this, memory network. So it's basically a recurrent neural net or a neural net that on the side is a separate memory, kind of an associative memory, if you want. It's sort of a hash table, kind of a soft hash table, if you want. And people have had this idea before for things like there's a technique called LSTM, which is also kind of a recurrent neural net with some memory on the side. This is sort of a different way of doing it. You might have heard of a paper recently published by people at DeepMind, Google DeepMind in London, called NTM, which is a neural Turing machine. It's kind of a similar idea, where you have kind of a neural net that sort of does the computation if you want, but there is a separate memory that's used as kind of a scratch pad. So this is the same idea. Okay, I'm going to stop here. I'm going to talk about Rajouni, that's another one I will talk. And thank you for your attention, and I apologize for being late and taking too long. Thank you.
Because of an Amtrak delay, we did have to start a little bit late, so let's take a few minutes for questions.